So today what we will do is we will have Jarrah come up and explain some of the radiation readings that were on the Polaris Dawn missions. The article that he wrote for ALICE was called Polaris Dawn Report, The Apollo Investigation by Jarrah White, or it's Apollo Investigation, Polaris Dawn Report by Jarrah White. Polaris Dawn did not prove that astronauts can survive the radiation on a flight to the moon. So, would you like to take it away, Jarrah?
Certainly. I have to say that I have been kind of distressed by some of the things that have been said in the media about the Polaris Dawn mission. There was obviously the media, they looked at the altitudes and they saw, oh, well, this is going to cross the inner Van Allen belt, and obviously they tended to jump on it and blow things out of proportion, and so something similar had happened previously with the Gemini 11 mission, and I felt it was time to step in and set the record straight. The Gemini 11, they started off with a circular orbit, a very low altitude circular orbit. Then they fired the Agena rocket to boost it into a more elliptical orbit, which allowed it to kiss the innermost edge of the inner Van Allen belt. Now, the belts, as I say in the article, the belts don't just suddenly stop and start as if you've just fallen off the edge of a pool and straight into the deep end. They start off shallow, proportionally. They start off very shallow, then they get more and more intense as you get closer to the heart of the belt. The Gemini 11 and also Polaris Dawn, they didn't get anywhere near the heart of the belt. All they did, as I said, they just kissed the innermost edge of the belt and then they dropped back down again. Gemini 11 did 2 of these highly elliptical orbits and Polaris Dawn did 6 of them. After that, they simply fired the rockets again and descended back to a more circular orbit.
Yeah, well, one thing that was interesting about this was about the radiation belt. Now, when Polaris Dawn was being put out there to the public, one thing that I did notice is that in the advertisements that they were running, they always showed the astronaut actually out there on a tether doing an actual spacewalk away from the capsule. But we don't see that. And another thing they said too was that they were actually going to enter into the very first radiation belt, which they never did, not walking in space. So I just wanted to throw that in there.
Yeah, well, like I said, all they really did was they just kissed the innermost edge of the belt. They didn't go much very far into that. That's been the whole Gemini 11 thing and the whole Polaris Dawn thing. They've both been blown out of proportion by people like Jay Windley and Phil Plait. Plait actually was in a debate with Joe Rogan, and I mentioned this in the article. He went so far as to claim, quote, the Gemini missions went deep into the heart of them and stayed there to make sure these guys could be in it. Well, that's false, because if they went into the heart of the belt, that would be suicidal. I have an actual graph from Kovalev, and he states very clearly that at the inclination that the Gemini missions used, the dose rates there are about 390 rem per day. That's at the heart of the inner belt. If you're going to be there for several days, that's going to be suicidal. Even a brief exposure at those kinds of readings is going to be suicidal.
Yeah, so just for the people that don't really understand this, can you just go over some of these values? Because some people don't really know what an MEV is. Like, for example, in Table 1, can you just explain briefly what MEV is?
Yeah, this graph here is purely for the 200 mega-electron volt protons. A mega-electron volt is the unit of energy. And so let me recall off the top of my head, 1 mega-electron volt is about 1.6 by 10 to the minus 13 joules. Okay, so basically we use that to determine each of these particles carries that much energy, okay, and we use that to determine, okay, so many particles have impacted the human body, they've deposited this much energy into the system, and so to calculate how much radiation a person has been receiving, there's absorbed radiation doses and then there's equivalent radiation doses. The absorbed dose is basically the amount of energy deposited in the body. Okay, we usually use grays, which is the amount of joules divided by the mass of the subject. You can convert those to rads. And then what you want to do is you want to then convert to the equivalent dose, which we do that by basically taking the absorbed dose and multiplying that by a radiation weight factor. For protons, it's 5, and for electrons and X-rays and gamma rays, it's 1. And so for photons and electrons, the absorbed dose is the same as the equivalent dose. But in the case of protons and the heavier particles, there tends to be much higher than the absorbed dose. And so what Kovalev showed in his table here is that for 200 MeV protons in the heart of the Van Allen belt, you're getting several hundreds of rem per day. Okay, and so this contradicted Plait's claim that, oh, they were able to stay in the heart of the belt for so long. Well, first of all, they didn't get anywhere close to the heart of the belt, and you can see that had they done so, it would have been suicidal. Again, it must be emphasized, all Gemini 11 and also Polaris Dawn did was simply make some highly elliptical orbits, basically changed from a circular orbit, made a high elliptical orbit, which basically took it within reach of the innermost soft boundary of the inner belt. And then they simply dropped down to the lower altitude again. You asked something about the spacewalking as well. This isn't mentioned in my article, but if you look at the actual videos of the, quote, spacewalk, it turns out to be more of a stand-up EVA because the guy had trouble getting out of the cabin. I believe we mentioned this on a previous show, but when I first saw the pictures, the unveiling of the spacesuits that they were using on the Polaris Dawn mission, I have to say, I thought, are they showing the right picture? Because they didn't look that much different from the pressure suits they usually wear during the launch and re-entry procedure of the mission. No. It looks like they just simply attached an umbilical cord to the launch and entry suit and just called it a day. By the looks of things, you can see he has trouble to move his arm. He can't really grab onto anything, and so he looks like he has significant restrictions in the suit, which might have limited his ability to get out of the spacecraft.
It is strange that these guys would be using those kind of spacesuits. One thing I don't understand, and we keep going back to this, so I don't want to harp on it, but the gaskets that sealed the faceplate to that helmet, the suit's all one. It's one piece that they put on, including the helmet. The whole thing is one piece. The one that I saw, because the fellow that was putting it on in the International Space Station, it was all one piece. And then they just clip the visor down. But it's just the gasket around the visor. I just can't see how a spacesuit that almost looks like spandex can do anything.
Normally what you have, you see, you would have a spacesuit you would wear just simply to maintain suit pressure when you're basically in the ascent phase or the re-entry phase of the mission. And then if you were going to do EVA, you would have a dedicated spacesuit for that purpose, which has relatively more mobility than the entry suit and the launch suit. But for whatever reason, as I said, it looks like they just simply used the same spacesuit and called it a day as far as functionality is concerned, and it seemed to be an afterthought. There's a YouTube channel called Common Sense Skeptic who has done some critiques on the Starship and a few of other Elon Musk's undertakings. During his unveiling of the Robin, he doesn't seem to pronounce Robo properly, but there was a particular shot in that unveiling in which he's accompanied by a guy in the spacesuit. Common Sense Skeptic noted that the guy couldn't even move his head because of the limited mobility in the suit. That there seems like a big design flaw. Even on the shuttle suits and the Apollo suits, they have a much, much larger helmet. So even though it's fixed in place, you can easily look this way and that to see where you're going, see where you can turn this and that, you know. So Musk seems to have this idea of making everything, let's just make it all look cool and futuristic, and whether it's functional seems to be an afterthought.
And another thing, too, that people were also saying about, well, why didn't they just take a camera out there and take some pictures and video? Well, they had a video camera in the helmet itself, so I guess they really didn't need that. But then again, they also didn't need any cooling tubes or heating tubes underneath the suits because they were hooked up to that umbilical. And I would imagine that the heat and whatever environment is required, plus the oxygen, would be in that tube.
I'd have to look into the specifications, but I believe they would have had some air conditioning tubing into the suit via that umbilical line. Usually what they have on the shuttle, and they started this on the Apollo missions, they would have these spandex suits with the water tubing, which would run through the suit to basically relieve them of the body heat. On Apollo, it was supposed to be vented outside the suit. When they were done with it, would then freeze to ice. And in the case of the shuttle, I believe they recirculated back into the suit. I also heard something about the modern shuttle suits being built like a thermos bottle to minimize the amount of solar heat to get inside the suit. But anyways, getting back to the article I wrote, we also discussed the South Atlantic Anomaly region in the belt, which of course is a region where the radiation dips much lower than usual. And this is one thing that the propagandists also particularly like to obsess about. They say, you claim the astronauts, they can't go to the moon because of the radiation belts. Well, what about the shuttle crews? What about the ISS? They all go through the South Atlantic Anomaly region. Well, here's the thing, right? The South Atlantic Anomaly region, first of all, the dose rates there are much lower than, say, the heart of the radiation belt. This was actually reported by Gautam Badwa, who was the radiation health officer at NASA. He's dead now, but he stated that if you go through the anomaly, the South Atlantic Anomaly, for 20 minutes, then for the remaining 70 minutes outside the anomaly, your body has time to do some recovery to the radiation. Now, Mary Bennett, she cited this in a previous Solace article she published back in 2002. When the propaganda saw that, it was obviously damaging to the false equivalence they were trying to push. Windley, he went so far as to deny that the astronauts have this healing ability. He says 30 minutes, not 20, as Badwa said. He says that sums up to 8 hours per day. The human body doesn't have chance to do that kind of recovery in hours. He said it takes several hours or days for the human body to do some repair to this kind of radiation damage. Well, Here's how you know that that's wrong, because we have actual measurements aboard the ISS and also the Mir station, right? It shows the South Atlantic anomaly delivers something like 0.6 rad per hour. And so if you expose by 8 hours a day, that ends up being something like 4.96 rad per day. And so you can do the math for how long the shuttle crews and how long the ISS crews have been up there. That ends up being several hundreds or even several thousands of rem in the long run. Well, obviously, no shuttle astronaut has ever received that kind of dose. So obviously, their bodies are doing some recovery to the radiation inflicted upon them, whilst they're outside the anomaly. So Jay Windley, he was just lying here on his website. He tended to embellish the whole story about Gemini, not just Gemini 11, also Gemini 10. He said, oh, Gemini 10 went into the main belt itself. Not just Gemini 11, but also Gemini 10 goes into the radiation belt. Well, Michael Collins himself actually disputed this in his book, In Carrying the Fire. He says that they only went as high as the South Atlantic anomaly, and I've shown various statements by him in that book. He says, this region, known as the South Atlantic anomaly, is where the radiation belt dips down, and at 475 miles will we be grazing at the bottom of it. Notice he says we're just grazing the bottom of the South Atlantic anomaly. He's not saying we're going into the heart of the belt, we're not going into the deep portion. He's specifically talking about the anomaly. And so if you want to get some ballpark numbers, on Gemini 11, it was reported that while they were skimming the innermost edge of the belt, they reported something in the order of about 0.2 or 0.3 rads. And so looking at the transcripts, we find that they're only in there for about 30 minutes grazing the innermost edge of the belt.
How many rads would kill a person so that we can have an idea in our minds what is going on with these other ones?
It generally comes down to the exposure time. A dose of up to 500 rem is considered to be lethal to astronauts, and so any radiation dose measured in several hundreds of rem is considered to be life-threatening. If you receive something like 200 rems over a lifetime, you'll probably end up with cancer. If you receive it in just then, you're probably likely to die very quickly soon after that.
Okay, then this is what I'd like you to do, and then we can go back into the article again, because I really love this one. Can you tell us, when you were in school, when you guys were doing the experiment with the radiation, with the paper and using aluminum, how when you got to the aluminums, I don't want to spoil it, but that was crazy. Could you just give us a breakdown of what happened?
Yes, when I was doing my astrophysics course, I'll never forget this. This was my first year in physics. Okay, we were given some copper discs, which contained different radiation samples, different radioactive sources. One was an alpha emitter, one was a beta emitter, an electron emitter for all intents and purposes, and one was a gamma ray emitter. And we had a Geiger counter. The idea was we would put the different discs in the path of the detector, okay, and then we would measure the counts per seconds, okay, and then they gave us little different pieces of material to use as shielding. We had a little paper piece, we'd have a aluminium piece and a lead piece. Okay, the idea was we'd see how many of those we would need to reduce the counts to zero, or close enough to zero as possible. Okay, you've seen many textbook diagrams where they show the alpha particles, the beta particles, and the gamma particles impacting different pieces of material. They'll show, okay, the paper will stop the alpha particles, the aluminium will stop the beta particles, and the lead will stop the gamma radiation. Obviously, what we did first, we needed some control. We basically put the alpha emitter, we put the beta emitter, and we put the gamma emitter in the path of the detector with no shielding. Here's what it looks like unshielded. We ended up having something like 1,000 or 2,000 counts per second for the alpha particles. So then we put the paper piece in there. The count rate dropped to about 2 or 3 counts per second. Okay, that was expected. This was a huge shock to me. We put the aluminium piece in there, in the path of the alpha particles. Intuitively, you would think, okay, if the paper stops the alpha particles, then surely the aluminium will do a much better job of stopping them. Lo and behold, when we put the aluminium piece in the path of the alpha emitter, the count rate was actually greater than the unshielded count. What was happening there? Well, it turns out as the alpha particle hits the aluminium, it ends up getting fragmented, because you see an alpha particle is 2 neutrons and 2 protons joined together. It's essentially a helium nuclei. As soon as it hits the aluminium, it just fragmented, and the detector was essentially receiving the secondary radiation, this breaking radiation, as the particle gets stripped into pieces and then thrown in at the detector. It went straight through the aluminium, was fragmented, and that was what we were just picking up. So we actually had a higher radiation level than we had with the unshielded.
But then back to the Apollo program, that's going to cook those guys in the capsule, isn't it? Because it's aluminum, the aluminium craft. And that goes for the space station that they tend to put up around the moon. So I don't know about that. But anyways, I digress.
Point is, yeah, normally what you would want to have, right, you would want to have a low Z material to stop the primary radiation. And then underneath that, you would have a high Z material like lead or something to absorb the secondary radiation. You'd have to put multiple layers of the aluminium or one layer of the aluminium and a layer of lead underneath there to stop the secondary particles from getting into the detector. That was our first-hand experience that we had in this physics class. The Polaris Dawn and the Gemini 11, we have the actual data from the mission. I actually was tuned into one of their live streams for a Polaris Dawn. Here's another thing that's quite interesting too. You see, if you actually look at the live stream and also look at the actual transcripts from Gemini 11, you find that when they did those highly elliptical orbits, they took place over Australia. This is significant because just much the same way we call the region where it dips the South Atlantic anomaly because, well, it happens over the South Atlantic. That's where the radiation dips to its lowest point. When it comes to the opposite side, the exact opposite is true. We have the much less radiation above my home country of Australia. Yay, Aussies, and so they specifically chose this particular orbit such that the highly elliptical thing would actually take place over Australia, where the radiation is at its lowest peak.
We're talking about aluminium at this particular time. Is not a Hasselblad camera made of that material?
They had a steel case, Scott.
Yeah, steel case, yeah. And
you sure not parts of it are made of aluminum?
Oh, the inner parts were. The parts where they mount. Because I have the whole thing.
Anything hitting that is going to excite the particles more and affect the film. The particles are going to fly apart and just be all over that film like crazy. And the cases, those ones that look like suitcases that they stored the box in to return the lunar rocks, those are aluminum. So what's radiating off the rocks, because they're irradiated, even though NASA says they're not, they're now inside the craft. Are they not going to magnify and enhance that radiation that they brought inside the craft as well?
That's an excellent point. Scott.
And they're sitting right beside it.
Marcus, you sent me an article a few years back about IMAX doing their film on their space station in which they had to use bags of water to protect the film canisters on their way back.
That's right, yeah. It was an interview with, I think, the producer of the IMAX film. It's about the construction of the ISS. They had 2 weeks. They sent the cameras up in the space shuttle. Then they filmed it as per the directions. Then they had to put the camera with the magazines still on board encased in the water containers. So it was protecting because they were fully aware that there were going to be problems from radiation. And this was the ISS. This is below the Van Allen belts. But they were protecting what they had available. And it was, 2 weeks they had to keep them up there before the shuttle came back down again. It was either the director or the producer of that film.
I remember, I actually have a copy of that film on DVD, and I found that quite interesting that they had to go to those lengths to protect it from the radiation that's below the main belt. The only real significant radiation they had to worry about was the South Atlantic anomaly, and all the other radiation they would get would come in the form of cosmic rays, the cosmic rays that managed to get through the magnetic field and whatnot. The magnetic field really protects us from much of the solar and cosmic radiation, and the atmosphere protects us from the rest of it. In space, you get a little higher elevation from what you would expect on the ground, and many International Space Station astronauts have received cataracts as a result of that exposure.
Something you mentioned a bit earlier about Joe Rogan interviewing Phil Plait. Do you know when that was?
That was in a debate they had on Penn Jillette's radio show back in, I believe it was 2005.
Okay. Yeah.
Yes, this was a couple of years, I think, after Penn and Teller did that despicable program with Plait and Renee. And from what I understand is they interviewed Renee for something like 3 hours. He obviously made the radiation part of his talk, and they cut and edited all over the footage and made it look like he was some drunkard. They had him drinking out of the vodka bottle, and he explained that he had his own water purification system, and he would use those bottles, whatever he had on his hand, vodka bottles, milk bottles, whatever, he would use those to keep that water purified in. As he said, they were shooting them and they weren't supposed to be shooting.
That was done some years ago, that interview.
The TV show that he did was in 2003, and the radio debate with Plait and Rogan was in 2005.
That makes sense. Thanks.
Yes. As I was saying, basically the Polaris Dawn and the Gemini 11, they both made their highly elliptical orbits over Australia, where the radiation is the lowest, which obviously is a good opportunity for them. And Polaris Dawn actually had something better going for it because it had a much higher orbital inclination. The higher your orbit is inclined to the equator, the less the radiation will be. It thins out towards the poles. And so the Polaris Dawn, they had the inclination of around 50 degrees, which is comparable to the space shuttle. In fact, I've actually got the numbers written down here, as a matter of fact, towards the end of the article here. It was 51.7 degree inclination, the same as the ISS. On the Gemini missions and also Apollo, there was more inclined to the equator by 30 degrees. That's significant as well, because if you actually look at the numbers like what's been attributed to Apollo 11 for its outbound trajectory, you'll notice that the orbit inclination, it never exceeds 31.16 degrees. Now, this is significant. I've got a textbook by Wright et al. 2005. They say the particle density is greatest at the equator and low latitudes, then decreases as the latitudes increase. This is for the inner belt. They say at latitude 50 or 60 degrees north or south, the density of the belt is very low. In writing about the outer belt, this is the electron belt, they say, like the proton flux, the electron flux is highest near the equator and becomes negligible at a latitude of 60 degrees north or south. Well, it becomes negligible at 50 degrees. Obviously, Apollo has a problem there because their altitude never got higher than 31.16 degrees, which demonstrates, for all intents and purposes, they should be right in the heart, in the most intense regions of the belts. I actually have the numbers that were actually attributed to the coordinates. I got the coordinates for the Apollo 11 mission. This was actually published by Robert Brainig. There's a whole story about that. Like Clayton Windley, he had his own pro-NASA Apollo hoax debunk website. After I was done with him, he deleted any mention of the Apollo hoax from his website, and you can probably get why. What he tried to do was he found the coordinates that are attributed to Apollo 11, the coordinates in terms of magnetic shell and magnetic field strength, B over B naught. What you can use is you can take those L and B over B naught values, you can plug those into the industry standard model for the radiation belts. That's called the AP8. AP8 is for the protons, AE8 is for the electrons. I could only really use the proton model because for the electrons, they don't have a model for any of the electrons that would actually penetrate the Apollo spacecraft. Their model stops at 7 mega electron volts, and so you need about 14 mega electron volts for the electrons to pass through the spacecraft. With protons, it's easier. We need about 8 mega electron volts to go through the spacecraft. First of all, let me tell you what Brainig did. He took these coordinates, plugged them into the AP8, and basically got the fluxes for each interval of radiation. And so then he said, the spacecraft, it'll stop all electrons up to 100 mega electron volts, and anything greater than 100 will go straight through the astronauts and won't do much damage. What? That's incorrect. To make this claim, he was citing data from this old report. I actually found his references. Okay, his reference was based on a graph from 1935, 34, something like that. Basically, when particle accelerators were in their infancy, back when we had very limited knowledge on what will shield and what won't shield. And as far as anything greater than 100 mega electron volts going through the astronauts, that's just wrong. For a direct comparison, in proton therapy, that's where we accelerate the protons to a certain level. So we're firing them through this pencil beam at the tumor. Okay, the idea with protons is that if you accelerate them to a certain energy, they only travel so far, and they tend to just lose all their energy at the maximum depth they can reach. They call it the Bragg peak. So you accelerate it such that the Bragg peak will be only as deep as the tumor, and then it releases all the energy there, it will kill off the tumor. That works fine for proton therapy, but in the case of the Van Allen belts, it's not a pencil beam. The entire body is being irradiated by these particles. It's all over the place. It's omnidirectional. The protons that we use in proton therapy are in the order of 200 mega electron volts. 200, 250, something like that. So that should give you an idea, right? And he's claiming that anything greater than 100 will go straight through the body. If that was the case, we wouldn't be using protons with energies up to 200 mega electron volts to penetrate a tumor.
Yeah, I was looking at this demonstration here, whereas the proton therapy, it stays inside the body. It doesn't go back out the other side, so it doesn't exit.
Exactly. So anyways, what I did then was I took Brainig's coordinates, found all the proton fluxes that I needed, and then I did the calculations to determine what would have happened. In fact, I actually showed the coordinates in one of my articles in column number 6 and also column number 5. Column number 5, that was for the proton fluences, which is where we're dealing with the total amount of particles from a solar flare. In the case of Article 6, I actually take the proton fluxes, this is in protons per square centimeter per second, and then I convert that into the rad per hour. Okay, so basically what you want to do is you get the proton fluxes, and this will be stated in terms of protons per square centimeter per second. Then I want to convert that to protons per square meter per hour. Okay, I got that. Then I want to multiply that by the surface area of a human, which is about 2 square meters. That cancels the area, and it gives me the number of protons per hour. This is the number of protons that have struck the human body every hour. Then I simply take the energy of the proton, multiply it by the flux I've got. That gives me the amount of energy per hour in mega electron volts. Then I simply convert that to joules. Then I divide that by the body mass of the human, and that'll give me the number of grays per hour. And you can convert that to rads. That's optional. I prefer to do that because it makes it easier to convert it to rem. Okay, so once I have my rem per hour, in the case of the Van Allen passage, we're basically just focusing on each minute of transit. If you look at the actual table, you'll see this is the time after translunar injection. So the graph shows that for the first minute of transit, that's when they first enter the belts, and it keeps going like that for the remaining 20 or so minutes. And so basically, I take that hourly dose rate, I divide that by 60, each dose for each minute of transit. Once I had my totals, the radiation ended up being something like 6.65 rads. Now, that has to be multiplied by the radiation weight factor of 5. This is something that I learned whilst I was researching this. I learned that for this particular orbit inclination, the AP8, even though it's the industry standard model, it actually has the tendency to underpredict the fluxes, because you see the AP8 is essentially just averages of satellite measurements made over the late 60s and the early 70s. This doesn't really take into consideration things like ejection events, like when there's a massive solar flare that can over-replenish the belts or create a third belt or this or that. The measurements have shown that for a 30-degree inclination orbit, the AP8 tends to underpredict the fluxes by a factor of 3. Okay, that's no problem. So I just take my doses and I multiply them by 3 to make the correction. So as you can see in the table here, for all the protons that would penetrate the astronaut's body and deposit their energy in the body, we find that the uncorrected dose would be about 33 rem, and the corrected dose would be about 99.7 rem. The reason I have two doses listed here is one is the skin dose and one is the body dose. The skin tends to receive the most brutal damage, you see, because obviously it's the one receiving the initial brunt of the radiation. It's sort of like a sunburn, you see. Just to put this into perspective, a skin dose of a few hundred rad is about enough to cause serious sunburn, and a skin dose of 2,000 rem is enough to require skin grafts. And so you can see from the numbers how severe the skin burns and the body doses would have been. So about 100 rem, that's life-threatening, as I said. In the skin doses, well, you think that would have been reported. They would go back, we had to rush the astronauts to the hospital because of severe skin burn surgery. Obviously, that never happened.
Yeah, but what gets me on Apollo is that they show such low radiation doses. Like, for example, here, you're looking at Gemini 11 here, I believe it is. Collins said that it was nothing more than a chest X-ray. Oh, I guess that's nothing more than a chest X-ray. Yeah, well, again, the context matters because they're just talking about the innermost edge of the belt on Gemini, the South Atlantic anomaly. Okay, for the most part, it's the South Atlantic anomaly. Only Gemini 11 had the high elliptical orbit that would take it within reach of the soft boundary, the soft innermost boundary, whereas on Apollo, they're supposed to have gone all the way through there. And in the case of Apollo 14 in particular, Apollo 14 has the highest skin dose reported. Again, I say skin dose, not the body dose. NASA only reported the skin doses because its orbit took it much closer to the heart of the belt. And that right there is an impossibility. I got this particular book here. This is Astronautical Engineering and Science. There's a section in here, Problems in Radiation Shielding of Space Vehicles by J. Warren Keller and his group of scientists from the Marshall Space Flight Center. They basically reported that the heart of the belt, you would need something like 100 grams per square centimeter of shielding just to bring the doses down to 1 Röntgen. The resulting shield thickness are seen to be quite formidable, with approximately 100 grams per square centimeter needed to reduce the total dose rate to approximately 1 Röntgen per hour. We use Röntgens typically for measuring X-ray and gamma ray exposure. 1 Röntgen is equivalent to about 0.87 rads. Okay, so you needed that, about a meter of shielding. If the material is water, 100 grams per square centimeter of shielding would be about a meter of shielding. Now, we're going back to the Van Allen belts because this is interesting what you said here about the planet. So the Van Allen belts are not constant about the planet being denser in some regions than others. High apogee orbits for Gemini 11 were therefore planned to take place over Australia because the level there is comparatively low. Now Conrad reported to Carnarvon, our dosimeter reads 0.3 rads per hour up here. Gordon amended this saying Houston radiation is revised to 0.2 rads per hour, to which Bean replies, sounds like it's safer up here than a chest X-ray. So how many rads did you convert that to?
You'd have to multiply that by 5 to convert that into rems. As I said, you would need something like 100 grams per square centimeter of shielding to bring the dose rates in the heart of the belt down to 0.87 rads.
But he's saying 0.3 rads per hour. That's nothing.
Yeah, like I said, this is just the innermost edge of the belt. He's not going into the heart of it. This is just for Gemini 11, where he's just skimming the innermost edge of the belt. You see, like if you have a diagram of the belt in a textbook, right, you can imagine, okay, Apollo would have to basically cut clean through that, whereas Gemini 11 just scream away at the innermost edge of it.
Okay, then let's go right into the heart of the Van Allen belts then. How many rads per hour are you going to get? For example, here these guys are going through there. Now they get right in the heart of the Van Allen belts. Let's just say they get right into the third belt. Like right in there, where the worst part of it's going to be.
Yeah.
Well, how many rads is that going to be per hour? What about gamma rays? Are they receiving gamma rays at that point?
The radiation in the belts primarily is protons. Okay, you will get gamma rays in the event of breaking radiation because, like in the case of X-rays are generated when electrons are stopped in material. They tend to lose their energy in the form of X-rays. With protons, when they collide with other particles, they tend to release energy in the form of gamma rays.
Yeah, the gamma rays are what we're interested in because that's what's going to cook them, right? The gamma rays are going to be basically being reflected all around inside of that craft.
That's why you tend to need a layer of high Z material underneath the primary shield to absorb the secondaries.
Yeah, the gamma rays are what we're interested in because that's what's going to cook them, right? The gamma rays are going to be reflected all around inside of that craft.
There's also a risk of neutrons. This isn't mentioned in my article, but I discussed it briefly in my Radiation Reloaded video. There'd also be a neutron hazard. It's mentioned in this book as well, as a matter of fact, this Astronomical Engineering and Science book, and that is that when you have the particles stopped in the shielding, you tend to get neutrons knocked loose of the shielding, and basically that becomes a secondary radiation in and of itself. That's why you tend to need a layer of high Z material underneath the primary shield to absorb the secondaries.
Yeah, but so what did the Apollo capsule have? They didn't have any walls. I mean, it didn't have any shielding or anything between the aluminum outside and the one on the inside.
I've actually got a picture somewhere. I found this on createspace.com, which is a space collector's website. Somebody actually had found an actual section of the actual Apollo hull. He had some photos with, measuring its thickness and whatnot. Basically, it had a layer of ablative material, which is obviously the stuff that burns away on re-entry. Okay, that's made of things like some epoxy and some other lightweight materials. Underneath that, there was basically honeycomb brazed stainless sheets of aluminium, which are basically honeycombed together. You see, you've got these sheets on the top and these honeycomb structure on the inside. Underneath that, you've got the same thing, but as steel. Okay, and so that all mounts up to be about 8 grams per square centimeter of shielding. And as I said, you need something like 100 grams per square centimeter of shielding to reduce it down to about 0.8 rads. It just demonstrates that they had no shielding. How the hell did they do it? That's the issue. We asked about what would be the dose rate in the heart of the belt. Well, as we showed earlier from Kovalev's article, he reports that at that inclination attributed to Apollo, in the heart of the belt, you're looking at about 390 rem per day, which is about 16.25 rem per hour. And of course, you can convert that to minutes and whatnot and see how much radiation they would receive. But then, of course, not just the heart, but the radiation on the way there, it all adds up, you see. And I showed in my calculations that they would have received something like 100 rem for the two-way trip. The first trip would have delivered about 72 rem, and the second trip would have delivered about 28 rem. You see, from what I understand, the return trip is supposed to be shorter than the first trip. And so it all adds up. It just doesn't come in the time that would give you some time to heal from this, as you would get from the South Atlantic anomaly.
Well, that's interesting because didn't Alan Bean say they didn't go out that far to get into the radiation belts? He had no idea that they were even there?
So I've seen some propagandists trying to pepper in the cracks. They say, oh, he must have been answering a question about Skylab. Well, here's my response to that. If he was answering a question to Skylab, he wouldn't, when told by what the actual dimensions of the belt were, he wouldn't have said, then we went right on out through them when he was told when they stop and start. Because Skylab didn't go all the way through them. There was a low Earth orbit mission.
I was looking at what Jay Windley was saying about some of the stuff. He's a poisonous chap.
Windley and I had a little discussion back in 2009. He was posting on the Internet Movie Database forum, and he's loved to lie about this ever since. There was a forum thread about Bart Sibrel's documentary. Windley was basically, posting his usual bullshit here and there. One of the things he was claiming is that Sibrel posed as a Japanese company to lure Aldrin to the motel so we would ambush him for that, and then when he was punched in the face. That's not what happened. Sibrel, he has often stated, he says this in his book, that this Japanese production company was doing a video about the moon landings, the moon landing hoax. They wanted to interview both Aldrin and also Sibrel. Sibrel was supposed to be a surprise guest. And Aldrin, he apparently quit the interview early when the topic of the hoaxes got brought up. And that's where he encountered Sibrel on his way out, you see. And in fact, what I found was there's a book by Aldrin, Magnificent Desolation. Now, this actually came out around the time this forum was going on. In his book, Aldrin, he writes that he did, in fact, give an interview to a Japanese TV company, and Windley is claiming in this forum thread that, I looked at police reports, I looked at prosecutors' reports that said that Aldrin was ambushed. Israel posed, quote, posed as a Japanese production company to lure Aldrin to the motel. I went into the forum and I basically said, well, how do you explain that when you got this statement from Aldrin? He dodged it like the plague, and I'd also called him out on his lies about, he claimed there was no major solar flares during the Apollo missions, and I cited the Comprehensive Flare Index for Major Flares, which is basically this list of all the, quote, major flares during the Apollo missions. He, rather than accept it as a correction, he just said, well, how many of those flares were proton events? At the time, I wasn't able to answer that question because I didn't have the records. The proton data on NOAA's website was from 1976 onward. I couldn't say which flares in the list were proton events because we didn't have that data on their website. Since then, I've managed to learn that at least one of the solar flares during Apollo 16 was a major proton event. And in fact, I did a whole article about that. That was my 5th column. We continued along these lines, and the moderators, they started deleting my comments, calling Windley out on his lies about Aldrin and about Sabrell. When it became clear that my messages would continue to be deleted, I just stopped debating it at that point. I just pretty much used it up for what I needed it for, I guess. And since then, Windley has lied through his teeth about that. He claims, Jarrah deleted all his posts after I owned him. I did not delete any of my messages. The only people who deleted my messages was the moderators, the administrators. And they claimed, he was posting profanity. No, I was not. In that same thread, he actually remarked, well, you're very polite to this time, Jarrah. I had encountered him once before then. I had joined a forum. I was under the impression it was a forum, but in fact, it was just another echo chamber. Casing had died a few months earlier, and let me tell you, I just let loose. Raw emotions. I was wild back then, but I would have handled the situation much better now, I think. But the point is, Windley has constantly lied about our encounters on the Internet Movie Database forum. He claimed that, Jarrah deleted all his messages after I proved him wrong. No, I did not delete my messages. The administrators deleted my message. He is being rude, he's being profanity. No, I was not. The only profanity in my messages was in quoting other people. And then he says, he deleted the thread. The Internet Movie Database, they've deleted the thread. Well, no, they haven't. They just moved it. He just lies through his teeth. And somebody actually joined the forum recently, called him out on that, and he's just avoided the topic. Even in the face of evidence to the contrary, he's continued to stick to his guns, basically, even after in the face of evidence to the contrary. Now, 1 year after that encounter on the Internet Movie Database forum, that was in 2009, it's ironic that he can claim to have seen prosecutors' documents and in the police reports and whatnot, because I've seen a few reports that concern him. Get this, apparently, a year after our little encounter on the Internet Movie Database forum, he was convicted for enticing a minor. He's on the Utah Sex Offenders Registry. I wonder why they've never discussed that on their forum.
Well, that is interesting because what you posted there, this is 5'4" and 135 pounds. Even a child could take him on, especially in this country.
His felony, his description is 76-4-401, enticing a minor / Class A misdemeanor. Date convicted, 19th of November 2010. Conviction state, Utah. Release date, the 29th of June 2011. Counts 1. I didn't even know what to say about that because that's just sick. And they say you should know people by the company they keep. Well, I think in the case of his echo chambers, we should know the company by the registered sex offender they keep.
Yeah, sex offenders in prison don't get a very easy time because other prisoners do not like people who fiddle with children. They normally land up in solitary confinement at best and dead at worst.
Then you also made another case here when you did column 6, or in the number 6 here, where did Dr. James Van Allen change his mind, or was it changed for him?
After the Fox TV show came out in 2001, Jay Windley, he quoted this passage from James Van Allen in which he says, quote, "The recent Fox TV show that I saw is an ingenious and entertaining assemblage of nonsense. The claim that radiation exposure during the Apollo missions would have been fatal to the astronauts is only one example of such nonsense." Now, I found the full article. This was a full email. He supposedly sent this to a guy by the name of Doug Lambert. He basically lists these 5 bullet points. And I basically went through each and every one of those. First bullet points, he says, the radiation shelves do indeed pose important constraints on the safety of human spaceflight. That's no dispute there. The next part, he mentions very energetic protons in the inner belt are the most dangerous and difficult to shield against. Specifically, prolonged flights, humans or other animals in the orbits around the Earth must be conducted at altitudes less than about 250 miles in order to avoid significant radiation. Well, this is true, but he sounds like he's talking about the South Atlantic anomaly exposure. prolonged flights, that would be something like the International Space Station. And 250 miles, that's closer to where the actual anomaly dips down to, so this doesn't seem relevant to what we're talking about here. The third bullet point here, he claims a person in a space shuttle would have to orbit the Earth at 1,000 miles for about 1 week to receive a fatal dose of radiation. Okay, well, hang on a second. That's not true. I actually got the AP8 readouts. I did the calculations, and I found that the space shuttle will stop protons with energies up to 10 mega electron volts. And so I focused on the energy greater than that. And when I did the calculations, I found it would be something like 50 rad per hour. And of course, you can multiply that by the radiation weight factor, and it ends up being something like 250 rad per hour. And so that indicates that an astronaut would not receive a fatal dose in a week, but rather hours. So he's talking complete nonsense here, to use his word. The fact that people continue to cite Van Allen's retraction demonstrates they never even bothered to fact check it. One course I did was planetary biology, where we basically look at the possibility of life on other planets. And one of the topics that we had to do was design a spacecraft to land on one of the moons of Jupiter. I basically proposed this elongated dragon-like capsule with basically a big driller thing to basically try to drill down to the water. Basically, there's a theory that there's a subsurface ocean there. I did a proposal basically have this spacecraft land this drilling thing so we can actually try to find some sea life or microbial life there. I went through all the trouble of discussing how to land this thing, how to shield the instruments from because the moon Europa actually lives in Jupiter's Van Allen belt. So you see the diagrams of that Elon Musk put out of his astronauts walking around in Europa. Well, how are they surviving the radiation? That's demonstrates he didn't think this through. But anyways, I went through all this trouble discussing this proposal to land this probe on Europa, what kind of instruments, what kind of experiments we could do to try to find life there. Extraordinarily detailed and everything. So many references, all this and all that, all these calculations and stuff. And I submitted that. I get 17 out of 20. And I said, why did I get 17 out of 20? I look at the examiner's notes. I forgot to discuss the communication system.
Oh my
God. You know what I thought you would have got nailed for? I definitely thought you would have got nailed because you didn't use boron nitride nanotubes as the material to disperse the radiation.
Yeah, right. I just found that one of the biggest highlights of getting my degree. I went through all this trouble designing the spacecraft to land on Europa, all these elaborate experiments, and I forget to discuss the communication system. This isn't a stable return mission. How would I expect to get the data back?
Yeah. Well, you see, if you take it from a Canadian point of view, it's just like ice fishing. You're going to drill down till you hit the water, and then you throw your line in. Mm. And if you get 17 out of 20, it's because you forgot to bring a Tim Hortons coffee with you.
Well, I'm happy to say that I asked a couple other reports that I had done. There was this one report I did on Australian tektites. Tektites are these glossy materials. You see, when a meteorite crashes into the Earth and sends up all this molten rock and glass up into the air, the glass portion actually crystallizes and comes back down to the Earth. Because of the similar chemical compositions to glass in the Apollo samples, there were some theories back in the 60s and the 70s that tektites came from the moon. Hint, hint. Anyways, I did this report on the tektites, and it's difficult to talk about tektites without discussing the lunar origin theories, and in my case, it's difficult to discuss those without voicing what I called my minority position about the moon rocks. And so I included a section about the rocks, why I reckoned that these things were faked and whatnot. And I was expecting to get marked down by that, but lo and behold, 100 out of 100. It had nothing negative to say, just, yeah, great report, 100 out of 100. I had a similar one as well where we were discussing they gave us 6 or 7 papers to read regarding the Allen Hills Mars meteorite, the one that was supposedly had nanofossils in there. Subsequent studies proved there was just a misidentification, and we were given these reports, proposing life in these rocks, and other articles basically debunking that theory, and we had to basically evaluate all those things, and we also had to find some other articles as well to cite in our report. I read somewhere that the meteorite was originally thought to be from Vesta. There's howardites, diogenites, and eucrites. The eucrite is your basalts, the diogenites are your gabbros, and your howardites are your breccias, these fragments of the things. These are all from Vesta, and the Allen Hills meteorite was thought to be a diogenite. And reading through those reports, I sort of started to lean in towards that original identification, and I voiced my views why as a little appendix at the end of the article. The examiner, he said 20 out of 20. Basically, he thought I made a good case that there's no fossils found in this meteorite. And he said at the end, I disagree with your Diogenite theory, but I appreciate the references and the research you did into that. What I've learned from that is that your peers, they may or may not agree with you in regards to a controversial theory, but it's important to make your case. That's basically what it all comes down to. You have to make your case.
Do you think we should, because you were talking about getting graded on the papers you provided that you developed and how you created landing on a different planet kind of thing, should we take that and bring it forward to Apollo, and we should start grading their papers on their simulated moon landing? Because there's so much stuff that they were missing. I mean, they forgot about communications. They forgot Collins was up there. They just forgot about him. They forgot the communication. So that brings them down. That already takes them to 17 out of 20 right there. I mean, if we start adding up the rest of it, they forgot about a countdown to take off from the lunar surface, knock another 3 points off them. They're going to have a failing grade in no time.
It'd be interesting to see. As a matter of fact, I'll tell you a story about that as well. One of my geology professors had actually co-wrote an article with Harrison Schmitt, first and only geologist on the moon. This was during my geophysics class. We went in separate cars. Basically, we took what's called a gravitometer, which basically measures the gravity field strength. We basically went off campus to basically try to detect these underground tunnels, these underground roadway tunnels. Okay, you can detect it by the gravitational strength. Okay, and so we went in separate cars. The person who was riding with the professor actually mentioned that I believe the moon missions were fake. And I kid you not, as soon as we got to the site where we were supposed to do the experiments, I'll never forget this. The lecturer, he says to me, "So, you don't like the moon landings, Jarrah?" And I said, "It's not that I don't like the moon landings, I don't believe they happened." And I kid you not, the whole field trip was basically just me and him back and forth arguing about the moon mission stuff. All my peers are like standing in the back, just sort of onlooking there, like I'm not getting involved, you know. And so we had this little discussions, and we would go back to our experiments. We would like put the machine down, we would do the settings, and while it's doing its readings, he would say, "Oh, by the way, Jarrah, what about this? What about that?" And I was citing all the counter reports off the top of my head. I had a very good photographic memory and stuff. He would say, "What about the fact that there's no water in the rocks? And what about the 6,000 parts per million of water discovered by Greenwood et al. 2010? You know, what about the water that was originally detected by Friedman et al. 1969? You know, all these things that this is comparable to the water contents of Earth rocks. What about ferric iron? About this?" You know, I was literally studying everything off the top of my head. He says, "You know, we have meteorites from the moon." And I said, "Are these the meteorites that were originally thought to be eucrites?" And, "Oh, you mean before we found the Apollo samples?" "No, after we found the Apollo samples." I mentioned, what was it, L-Moraine 8452, all these different, I was reciting the names of the rocks in question. I was just, this is supposed to be a learning experience. And literally all I remembered from that field trip was just me and him back and forth about the rocks. You know, I guess they sort of take it kind of personally. I guess he would probably take it even more personally, considering that he, you know, wrote a paper with Schmitt.
Yeah, it's probably the first time anybody had been seen to challenge what his hero Schmitt had been doing.
That's another thing with the Jay Windley thing, because first of all, there's no disclaimer. You know, Rogan has since claimed, "Oh, it was just done for artistic purposes, you know, as a illustration type thing." Well, first of all, there's no disclaimer in the book about that. There's no, you know, disclaimer that it's intended as an artistic purpose. But Windley, he often went so far as to claim that Ralph Renee was offered $10,000 by Jim Oberg to prove that Collins did indeed intend to claim this as a Gemini 10 photograph. Well, there was no such. I actually contacted Ralph Renee and asked him about this, and this was news to him. He was like, "What? He offered me?" He was completely shocked. "He didn't offer me shit. We went to war immediately." Those were his words. You know, and so that demonstrates that Jay Windley, he's not interested in the truth. He just has this agenda to make those who disagree with him look dishonest by any means possible.
Okay, so he also added that a lead shield rated at 4 grams per centimeter only mildly reduced the proton dose rates he recorded. What is this? What were you talking about here? I didn't know that Apollo capsule had a lead shield in it.
This is what Van Allen had wrote in his article. This is his 1961 Space World article.
Yeah, okay, there we are, yeah.
This is from 1961. Apollo didn't have any lead shields. He's talking about the various satellites and space probes they sent up into the radiation belts. He reported a lead shield rated at 4 grams per square centimeter would only mildly reduce the proton dose.
But then he has here, while the stainless steel and ablative material was rated at 7 to 8 grams per centimeter.
This is what I reported here. This is what I write in the article. I write, Van Allen, he also added that a lead shield rated at 4 grams per square centimeter only mildly reduced the proton doses that he recorded on his spacecraft. And I say, by comparison, the Apollo spacecraft had a shielding of aluminium and stainless steel and ablative material rated at 8 grams per square centimeter. And of course, Keller, they reported that you need up to 100 grams per square centimeter of shielding to reduce the proton dose down to approximately 1 Röntgen per hour.
You see, this is what's confusing people. You have protons, then you have gamma rays, then you have X-rays, then you have REMs, then you have rads, then you have becquerels, then you have sieverts, then you have you have to do a lot of mathematics just to get back to the REMs or rads.
And context matters a lot, you see, because sieverts and REM, they apply to the equivalent dose. Rads and grays, they refer to the absorbed dose, and as I said, the absorbed dose, that's the amount of energy deposited in the mass. Okay, to convert that to the equivalent dose, you multiply that by the radiation weight factor, which depends on the type of radiation that's radiating the subject. One must be very careful how you use these terms because context matters.
Yeah, but these guys are throwing this all over the place, and I think it's almost like they're doing this to confuse you.
I got my little table here. For absorbed radiation doses, we use grays and rads. And of course, the grays can be divided to about things like milligray, millirads, and things like that. For the equivalent dose, we have the sieverts, the REM. REM specifically applies to humans because it's Röntgen equivalent in man. And when it comes to exposure purely from X-rays and gamma rays, we talk about Röntgens or coulombs per kilogram. I tend to try to stick with the units that most people will be familiar with, or most people who are versed in stuff will be familiar with anyways, like the rads and the REM. But of course, people tend to use rads and REM interchangeably at times. I plead guilty to doing that myself in the beginning and stuff like that, but I like to think I'm able to catch myself and make sure I use the correct terminology now.
For example, now, just to keep it simple for the layman, what level of REM would kill you?
500 REM in any short time is considered lethal to humans.
Right, and then let's go to grays.
That would have to depend on the type of radiation that's affecting you see, because a gray is basically the amount of radiation that's deposited in the body. Okay, so you find out what the effect it would have by converting that to REM. 500 REM is considered lethal. If it's protons, then it's the absorbed dose multiplied by 5. If it's X-rays or gamma rays, then it's basically the absorbed dose multiplied by 1. So 100 grays would be about 10,000 rads, okay? And so, you can do the math there. If it's 10,000 rads of X-rays, you get 10,000 REM of X-rays. If it's 10,000 rad of protons, then you get 50,000 REMs of protons. Like I said, it all depends on the type of radiation that's affecting you. You got to make sure you're using the correct conversion factors.
Right, and then last but not least, the sievert.
For the record, 100 sieverts is equivalent to 10,000 REM.
Can tortoises withstand much more radiation than humans can?
Indeed they can. I have an article that discusses them absorbing things like tens of thousands of Röntgens versus a few hundred for humans before it will kill a turtle. Again, we can't really use REM for turtles because the REM is not applicable to non-human life forms. We can use rads, of course, or Röntgens and stuff, but in the case of humans, it's measured in the hundreds, whereas in tortoises and turtles, it's measured in the thousands. That's another thing that Windley likes to bring up on his website. He brings up the Zond 5, which sent turtles and insects and some plants and whatnot around the moon. And he says, these life forms have survived without all these layers of shielding and whatnot. Well, they didn't quite need it because they're more resistant to humans. Anything that's more resistant to humans, we call them extremophiles. In the case of turtles and these insects, we consider those to be radio-resistant extremophiles. And in fact, the plant in question that they brought on Zond 5, that was a spider plant, and I find that very amusing that he would cite, this spiderwort plant can survive the radiation. You know what the nickname for spiderwort plant is? A living Geiger counter. That's its nickname because you expose the spiderwort plant to extreme amounts of radiation, only its stigmas change color. It doesn't die or anything like that.
So obviously people like Windley don't really understand the radiation measurements and how they're doing.
Or he's hoping his audiences don't understand it.
Well, what we're trying to do to separate out the problems and show that humans are affected by radiation quite severely. We're not designed to be in space. We're delicate little creatures, us humans. We should look after ourselves and not put ourselves in danger, like going to the moon. It's not wise without the necessary protection.
What kind of a spacesuit would you have to design in order to actually walk on the surface of that moon and not die of radiation poisoning?
Well, realistically, you wouldn't be able to have have a kind of suit like that, you would probably use something like a mech suit or something to try to just bring it down to reasonable levels. The idea is if you're walking on the moon, you want to constantly monitor your personal dosimeters and basically see, okay, what's the readouts looking like? On the Concorde, for example, when they were doing polar routes, they would always take evasive action away from the poles in the events that it exceeded something like 100 millirad per hour, because like that would be an indication, okay, there's a massive solar flare happening, we should drop to a lower altitude or take evasive action altogether to minimize radiation exposure. Okay, and so realistically, you probably want to do something similar. If you're out on the moon, okay, the radiation is getting high, there must be a solar flare coming, I must retreat to my shelter. The idea is you would have a shelter, a little base there, basically buried underneath all the lunar material to try to maintain some form of shielding. Erica Harnett, she proposed actually timing a mission to the moon such that it would coincide with the full moon. The idea is that during the full moon, the moon will actually enter the magnetic tail of the Earth. You see, the Earth has a magnetic field. That's where it traps the radiation in those magnetic field lines. At the same time, the solar wind blows the magnetic tail back further out into space. You see, it's this enormous tail. They call it a magnetotail. Okay, and during the full moon, the moon will actually enter this tail. There have been some proposals to actually time the mission to the moon such that the spacecraft will go up the tail, receive the same protection from solar flares and the like by this tail, and then land on the moon while the time it's in this tail. Obviously, do your business out on the moon under the shielding of the tail. Once before it's scheduled to leave that tail, launch off the moon and go home.
So then they would have to basically dig a tunnel into the side of a hill, like a mountain or something like that, and then go in there and shut the door?
Either that or have it built inside a lava tube. There are naturally forming lava tubes on the moon, and there have been proposals to drill under there as well.
Another question I get is, would Elon Musk's suits that they did the EVA in on the Polaris Dawn, would that function on the lunar surface?
No, I don't think it would function on the lunar surface as a radiation shield, but based on the limited mobility of his suit, I think it's more geared for maintaining suit pressure during launch and re-entry, if in the event of there's a cabin depressurization like he had on Soyuz 11. Going back to what Common Sense Skeptic actually showed in his video, when they had the Robovan or Robovan, whatever you want to call it, he was accompanied by the guy in the spacesuit. He seemed to be able to walk around better in sea level atmosphere. But even then, he couldn't really move his head because of the there's no neck ring or anything like that on the spacesuit. Like I said, Musk seems to be more concerned about making the suits look cool rather than making them functional.
Just one point on the visor. Obviously, a visor being pulled down like a motorcycle helmet, the visor's pulled down. If you've got internal pressure in the helmet, which you would have, wouldn't that force the visor out and allow all the air inside to basically be removed from inside the spacesuit? Or is there an internal helmet that is secured to the top of the spacesuit and the visor is just the protection from the bright light?
That's correct. The inner suit, there's actually 3 layers of the visor. There's what they call the so-called fishbowl helmet, which basically connects over the actual neck ring and basically maintains the suit pressure. Over that is essentially this outer helmet, which has the outer layers on it. You have the inner clear visor, which seals in the suit pressure. Then you have a outer red visor, which is protection against micrometeoroid impacts, as they say. And then there's a outer gold visor, which is purely against UV protection. It's basically like a gigantic set of sunshades.
Okay.
Yeah, but that's the Apollo one. I have my own theory on that. That little neck foil that goes around there, I believe that whole thing is actually vented. The only point where they have an umbilical is down on the leg. If the air is blowing through that, and for that helmet to stay clear without fogging up while they're breathing, it has to vent out from somewhere. Don't forget, these suits were created by Joe Fernandez, a Hollywood costume designer, designed these things. When they're sitting down and you see where the umbilical's plugged in, they're virtually cutting the air off coming into that. If they're bringing air in and controlling the air and the temperature in that suit, it has to have an exit to be able to control everything in there. That's just a minimum. So it has to have an outlet. And when you look at the banding around underneath the helmet, I believe that's just a vented material, just a soft vented material that it's able to flow out of there. That'll keep them breathing properly, everything else. That helmet, when they pull it down like a motorcycle helmet, that's on a rubber seal. Yeah. Number one, rubber won't work, period. When you're at 10 to the minus 12, you can't use rubber. As soon as you see those features and they document that, then we can grade them and say, no, you can't have that. So we're going to have to knock 5 points out. So now it's only 15 out of 20. And when it folds down like that and doesn't have an interlock, it would have to be screwed down. You take a look at how Bill Demos puts his vacuum chambers together with 8 bolts around. It would have to have 8 bolts and they'd have to be torqued down to create that seal. And that's the bottom line. And when you see it like that and it doesn't have it, then we're going to have to take another 5 points off. Now it's 10 out of 20. And this is how you rate them. And because they didn't use anybody, a costume designer, now they're down to 0.
I really have a question for Jarrah. When we had a talk with Bill Demos, he's the fellow that does the physics and the electronics at the University of Patras in Greece. So we put this question to him. You have a vacuum chamber down here, and you can bring that chamber down to torr 10 to the minus 6, and you go into space, you go above the atmosphere, keep going. There we go. We're at torr 10 to the minus 6. Now you're in both places. It's equal. Why is it that you do not need metal seals there, but you do in the vacuum chambers on the Earth? It's supposed to be the same place because you're going out, 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 out. That's almost like you're slowly removing the air from the vacuum chamber like a pump. Mm-hmm. You're slowly going out until there's pretty much nothing there. And why would you need these seals? I mean, it's crazy. So when we're talking to a guy that has a Bachelor of Science with honors in this field, and he's saying that that's the reason why he has to use metal seals, one-time metal seals, by the way. He says it'll work up to torr 10 to the minus 6. Anything beyond that, if you don't use a metal seal, it will not work. It will leak. In other words, they're out there, they're docking, the LEM comes up, it docks with the command module, and on the moon, out that way, it's torr 10 to the minus 11 to 12. So how are those spacecraft coupling without using these one-time metal seals? This is another mystery I've never been able to figure out.
I'd have to look into what you're talking about, the actual seals themselves. I'm not quite sure which ones you're talking about, but the on Apollo, supposedly what they had to do was they had the probe and drogue, which they had to manually take out and insert back into the tunnel. The transfer tunnel was what they were supposed to be using to actually dock the spacecraft with.
But wasn't there rubber around there to seal the air?
I would be surprised if they didn't have that kind of stuff, which I haven't looked into this subject myself, but I would have to look into that particular topic.
Because, see, this is something that nobody can answer. I mean, we've asked Bill. He's explained it, and it makes sense because he has a Bachelor of Science with honors in that field. But if you ask anybody else, like you ask these numpties out there, they have no answer for it. And then you say to them, for example, well, it's the same place, isn't it? Well, if you have minus 6 down here and you have minus 6 there, isn't it equal? Well, of course it is, because water and blood boil in the same place. It outgasses.
Yeah, and then if you see Bill clean up his equipment to make it seal, and then we have astronauts climbing over a door frame with lunar dust, regolith, all over the place. How is that door ever going to seal? And that's his one thing. Then we can add one more item to it. The bloody machine is sitting with one side to the sun and the other side's to the shade the entire time. The temperature differential is going to warp that aluminum. There's going to be expansion there. That door wouldn't seal because it won't fit anymore, just because of the temperature differential on there. So there's just 3 factors there on it. So they get 0 out of 20 on that project as well. I mean, we're just going to keep rating them.
I just found this one article here. This is actually a paper, rather. Apollo seals, a basis for crew exploration vehicle seals. They're talking about building seals for the crew exploration vehicle, as was known back then. Now it's called Orion, obviously. Basically, they say the CEV resembles a scaled-up version of Heritage vehicle. Seal requirements are different to those in Apollo.
Like I said, all the testing they've done at the Sandusky chamber with Joyce Deaver on all the different materials she put in the vacuum chamber. We have images already of rubber seals put in the vacuum chamber and see the distortion and swelling that happens to them.
Speaking of rubber seals, you guys were talking about the Challenger disaster on the previous program a couple of weeks back. I actually managed to interview the guy who actually looked at the seals on the Space Shuttle Discovery in the build-up to the Challenger disaster. I have a whole video about that on my channel. His name was Roger Beaujolais. He basically reiterated all the things that had gone, wrong leading up to the Challenger disaster. Basically, the way the solid rocket boosters work, normally when you want to build a solid rocket, you would have one single tube filled with the solid rocket, and you call that a day. You would have those shipped over by a barge, over to the Cape. But because the contract for the solid rocket boosters on the shuttle went to Utah, they had to be basically divided up into segments and basically shipped via rail, and then basically stacked together like a Lego set in the vehicle assembly building. Now, basically, the seals, they clamp together like this, you see. You've got a tang and a clevis, and because of the fluctuations in the propellant, it's going to be buckling this way and that as the rocket is burning the propellants and taking off. And so you want to have an airtight seal. They would use a zinc putty to try to seal it, and as a backup, they would have these O-rings, which would basically fit into there. The idea is that if you were pushing out on the O-ring, it would compress the O-ring, prevent the gases from getting out. If the thing pulled away from there, the O-ring would expand out because it's a pretty big O-ring. It would expand and then would just block the seal. Okay, that was the plan, but in practice it turned out the primary O-ring could fail, or fail in parts. The first 14 flights had a little damage here, a little damage there, as Beaujolais said, but on the 15th flight, which was the Discovery launch, and ironically enough, Ellison Onizuka was on that flight. Okay, one of the astronauts who died in the Challenger disaster, he had a precursor to his brush with death. Basically what happened was it was very, very cold on that particular launch. This was in January of 1985, and it was about 53 degrees Fahrenheit. When they got the boosters back from the mission, Beaujolais, he was inspecting the damage, and he found that the primary O-ring had failed completely, and it allowed massive amounts of hot gas to get past the primary seal. Fortunately, the gases, they didn't escape to atmosphere because the secondary seal did its job, but this demonstrated that the primary seal could fail completely. Okay, and so the discriminator, he believed, was the cold. He remembered seeing on the TV the day before that the weatherman was reporting temperatures up to 53 degrees Fahrenheit. The citrus crops were going to be destroyed and the citrus trees would have to be replanted because of the cold. He presented his findings to Thiokol. He was asked to present these to NASA, basically show that the photographs, he showed him the swabs that he used to take samples of the blackened grease that had occurred. And he says, I believe that the temperature was the discriminator.
NASA did their best through a series of many, many half-truths and some outright lies to make it sound like it was an accident. And that's bullshit because it was a horrible disaster, but not an accident. When you got people that are your technical experts jumping up and down, raising hell, trying to stop the launch, and being ignored, you can't then, when something goes wrong, turn around and say it was an accident, or it was a bad judgment call, or this or that. Listen, I want to tell you that I was held in such high esteem. At this point in time, I was the technical troubleshooter on the solid rocket boosters concerning the structural cases. I had nothing to do with propellant or the nozzle, but those cases were my baby. And when something went wrong, it was my job to make damn sure that the trouble was ferreted out and fixed. And the decisions that I made carried a great deal of weight, except on the night that we were trying to stop the Challenger launch. By that time, it didn't matter what the hell I said, because they had already made up their minds before the telecon started that they were going to do everything in their power to make us back down so that they could get an approval for launch. When I did that inspection on the two boosters on the 15th flight, 2 out of the 6 joints had massive hot gas past the primary seal. And although none escaped to atmosphere, as indicated by a pristine secondary seal, which had worked in both instances, we had never seen anything like this before on any flight.
The discriminator, he believed, was the cold. He remembered seeing on the TV the day before that the weatherman was reporting temperatures up to 53 degrees Fahrenheit, and that the citrus crops were going to be destroyed and the citrus trees would have to be replanted because of the cold. He presented his findings to Thiokol. He was asked to present these to NASA and basically show that the photographs, he showed him the swabs that he used to take samples of the blackened grease that had occurred. And he says, I believe that the temperature was the discriminator. They did some preliminary tests with steel plates and some O-rings themselves, trying to mimic this, what could have happened. They also found there could be seal failures at room temperature, but at the much colder temperatures, you would get much more blow-by, much more blackened grease, much more gases shooting past the primary seal. Now, a couple months later, there was another incident. I think it was the 17th flight, there was a faulty leak check and the primary O-ring failed and eroded the secondary O-ring. And this prompted him to write this report, which he submitted to his superior. His name was R.K. Lund. And basically said, what happened here is this primary O-ring failed and the secondary O-ring in the nozzle joint was eroded. And he said, if the same thing should happen in a field joint, you see you got the field joints and you got the nozzle joints. He said, if the same thing should happen in a field joint, then it's the jump ball as to the success or failure of the joint, because the secondary O-ring cannot respond to the clevis opening rate and may not be capable of pressurization. The result will be a catastrophe of the highest order, a loss of human life. And he wrote that in July of 1985. He sent that off to his superiors. This was stamped company private, so he couldn't really share this with NASA or anybody else, you see. But what he did do, he took a copy of that and he whited out the company private and showed it to some of his close colleagues. He didn't give them a copy, just let them read it. And basically, he wanted them to know that he had put his management under full written notice that if they didn't solve this problem, they were going to be basically playing Russian roulette with the lives of the astronauts. I haven't posted this on Alice, but I've posted the interview with Beaujolais on my YouTube channel. And so basically, then Challenger comes along. This is a year after the Discovery incident, which we had the 53 degrees Fahrenheit launch, and they're concerned about launching in freezing weather. They get a phone call from some guy down at the Cape asking, are we concerned about launching in cold weather? When Beaujolais heard that, he went nuts. And so they got their superiors together and they telephoned the people at NASA, basically saying, we don't think it's safe to launch in cold weather. Now, I need to pause for a second and basically explain how these pre-flight hearings actually work, you see. Normally, NASA, they speak to the contractors. They say, are we safe to launch tomorrow? Or are we safe to launch in this particular time? They say either yes or no. If they say yes, then NASA basically interrogates the contractor, basically makes damn sure that they are very 100% confident in what they're saying, make sure they are very clear in their recommendations, make sure they're on very, very firm ground. Normally, if they say, no, we're not ready to launch, NASA says, okay, launch is cancelled, we basically postpone it to later. This time it was the reverse. When they say we don't believe it's safe to launch in cold weather, NASA said prove it's not safe to launch. And so they wanted this full-blown flight readiness review within less than an hour. And so Beaujolais and his colleagues, they all grabbed whatever pieces of material, whatever papers, whatever photos they could to basically present this report, present this presentation over the phone, have them faxed to the people at NASA. There was the people at the Marshall Space Flight Center and the Kennedy Space Center, and they basically presented all this material to them. And normally if they say we're not safe to launch, that's the end of the matter. That's the end of the discussion. But now suddenly there was a debate about it, about not being safe to launch in cold weather. They presented these findings, and the head guy at the Marshall Space Flight Center, his name was Larry Malloy, he started saying things that the data was inconclusive. He challenged them to try and prove that. When he asked for their recommendations, first of all, the first recommendation came from Joe Kilminster at Thiokol. Beaujolais, he had about a 50% confidence that Kilminster would stand by their original data because he's sort of a wimp. Beaujolais told me he's sort of a wimpy manager, you see. But to his surprise, he said to Malloy, our position is we do not feel comfortable launching at a temperature below 53 degrees Fahrenheit. Okay, so that's the first no vote to launch. And Malloy, he wasn't happy with this decision, so he basically turned to George Hardy, who's a NASA guy from Harding, from Marshall Space Flight Center. Beaujolais actually explains to me, he says, people on the outside, they don't know who George Hardy was, but he was basically at the Marshall Center years before NASA became an agency. No, he was basically like the Desmond Llewellyn of the Marshall Space Flight Center. He'd been there from almost the beginning, you see. And so his decisions carried a great deal of weight. His recommendations, his thoughts on this, and he had basically said he was appalled by the no-launch recommendation. Yeah, but at the same time, he also added, I'm appalled by this no-launch recommendation, but I can't overrule the contractor. So basically, he would only agree to launch if the contractor said it was safe to launch. And they just said it was not safe to launch. And Malloy, he basically says something to the extent, why are you guys trying to come up with launch commit criteria on the eve of the launch? When do you want me to launch next April? Now, during the investigations that followed, the Thiokol managers, they would say that they felt no pressure. They felt no intimidation.
You didn't feel that they were trying to get you to change your mind?
I did not feel a significant amount of pressure in that regard.
Well, I'm telling you that's absolute 100% pure bullshit. Because if they felt no pressure, why did they think it was necessary to convene a caucus to reevaluate the data? They felt pressure. Everybody in the room felt pressure. I felt pressure as a major presenter, as an engineer, trying to stop the launch. And I was crushed when they asked for the caucus, and it was granted.
After Malloy starts making these statements about when do you want me to launch, in April, Thiokol managers, they requested to go offline to reevaluate the data. And it was clear from what they were discussing, the Farcom managers, that they were basically trying to sketch out some reasons to justify a launch. Because their next contract is still under development, you see, and they feared that their contracts could be in jeopardy. When it appeared like they were changing their minds, the engineers tried to intervene to try and make them stick to the original recommendations. His former boss, named Al Thompson, he gets up and basically sketches out a field joint, basically explaining the dangers of launching in the cold weather, and they just ignored him like he wasn't even there. He was so pissed off by the way they treated Arnold Thompson that Beaujolais, he got up, he slammed the photographs on the table. He had two sets of photographs. He had the photographs that he had personally taken of the 53 degrees Fahrenheit launch, and he had a second set of photographs, which was from the 22nd flight, which was room temperature. Okay, the 22nd flight had some blow-by here, some blow-by there, some little black stuff, and whereas the 53 degrees Fahrenheit launch was just completely black. Blow-by had shot past the primary seal.
I mean, it was clear that the gas past the seal on Flight 22 at room temperature wasn't anything even close to the volume of gas past the seal in the 15th flight at a seal temperature of 53 degrees.
He was told after the thing that he was literally screaming at the managers, basically telling them to look at the photographs, and that the more black you see in these pictures, that's the low temperature. That's the effects of low temperature. The colder the temperature, the more blow-by you're going to get. And now we're talking about launching in freezing weather, a condition where neither the primary seal nor the secondary seal is going to function. They ignored him just like they ignored Arnold Thompson. And so when it was clear he wasn't going to listen to, he just sat back in his seat and, sit down and shut up, and was basically trying to just really contain his anger, because he felt like he could have just punched one of those out at that point. Yeah. The Farcom managers, they decided amongst themselves. They had a vote amongst only the four managers. The vice president of engineering, he was the last one to make the vote. And his superior actually told him to take off your engineering hat and put on your management hat. Okay, and so eventually they all agreed to launch. They went back on the line. They told NASA, okay, the recommendation is go for launch. And to NASA, that wasn't even good enough. They wanted it in writing. They had them fax a written agreement to go to launch, and they had sketched out all these reasons where they used to justify it. But if you look at the actual recommendations they have, there's literally nothing on the page that can justify a launch. In fact, it's literally much of the same things that they brought up beforehand, and there's some outright falsehoods that were added there. Like they say, engineering assessment has concluded, yada, yada, yada. Well, there was no engineering input in regards to making this decision. It was purely managers amongst themselves.
I was just going to say something just for clarification for people that are listening. The temperature during that night before the launch was down below freezing. At 11 o'clock in the morning, they're still waiting for the ice to melt off of the vehicle. Mm-hmm. So the vehicle itself was still frozen, and it was 36 degrees Fahrenheit or 2 degrees Celsius at launch. So that's well below the 53 degrees where they're already showing some serious problems.
The engineers who were objecting to the launch, obviously there was Beaujolais, then there was Arnold Thompson, there was another fellow by the name of Bob Ebeling, and then there was Brian Russell. He's the youngest of the engineers. He only said about 2 words during the thing. He was the youngest presenter. He was the guy who presented the pictures from the 22nd launch. And over at the Cape was Al McDonald, who was the first whistleblower. You see, after the Challenger disaster happened, NASA, they acted as if the only recommendation to launch was it was safe to launch. We contacted Farcom, and they said it was safe to launch. They never said anything about the initial launch. It was actually Al McDonald who basically raised his hand up and basically interjected and saying, our original recommendation was not to launch. And so after that, McDonald and also Beaujolais in particular, because he actually presented the smoking gun memos basically showing that they were concerned about launching a full year before the Challenger disaster, and they all got treated as whistleblowers. In fact, they started to refer to themselves as the 5 lepers because they were treated as if they had leprosy. No one wanted to touch them anymore, you see. One of the things that strikes me, particularly what Beaujolais actually said in his interview to me, he told me the managers, they went ahead and committed to a launch knowing full well they were playing Russian roulette with the lives of the astronauts.
They went ahead and committed to a launch knowing full well that they were playing Russian roulette with the lives of the astronauts. Only the type of Russian roulette they were playing was, instead of having a 6-gun with 1 bullet in the 6 chambers, they had a 6-gun that was loaded with 6 bullets, and they were praying like hell that when they pulled the trigger, the gun would jam.
Those were his exact words. I couldn't believe it.
Yeah, that's much the same as the conclusion that Richard Feynman reached. He was on the Challenger inquiry, and he made the rather sensible decision to go and speak to the actual people who were assembling these solid fuel boosters and asking them, not their managers, who were all gung-ho and trying to do what President Reagan at the time, who was promoting this idea of sending a civilian teacher into space. So it's all a PR exercise to begin with. And Richard Feynman's famous last sentence in his report, which had to be included separately as an appendix to the Challenger inquiry, because they wouldn't accept it, despite the requirements of PR, nature cannot be fooled. And you've described why nature cannot be fooled. If it's too cold, things don't work.
Yeah. As Beaujolais put it, this is not rocket science. This is literally engineering 101. As he said, you could present this stuff to a housewife and it would be perfectly clear. I go a bit further and say you could go on Sesame Street and present this in very simple terms and the kids at home watching will get it. And we got these managers with decades worth of experience behind them and they don't seem to grasp that this is a problem. Beaujolais mentioned something else during his interview to me, in that if he had gone public with his company private memo, he would have been released, and that release would have come not from Thiokol, but from NASA. You see, the head of the Marshall Space Flight Center, the director there, his name was William Lucas. As Beaujolais put it, he ran that division like it was a Gestapo prison camp. He said he wasn't exaggerating when he says that because he had the authority to reach into the contractors and basically crush people's careers. And so people were very, very scared to speak up about the problems that they were experiencing because Lucas had basically said the Marshall Space Flight Center would never, ever, ever be held responsible for delaying a flight. And so he had put a great pressure on people to, sweep things under the rug and make things look more rosy. This isn't exact words. I've never had to do this before in an interview, but I actually had to ask somebody if I could quote him on this because Beaujolais, he said to me, after he reiterated what Lucas had basically declared, that they would never be held responsible for delaying a launch, Beaujolais remarked, "That is sick. A guy like that should have been taken out and shot right on the spot." I was absolutely astonished when Beaujolais said that, and I said, "Can I quote you on that?" And he says, "Sure you can."
He had his people under him scared to death because he could crush their career in a heartbeat. And he had basically stated that the Marshall Space Flight Center would never, ever be responsible for delaying a launch. Now that's sick. A guy like that should have been taken out and shot right on the spot.
Can I quote you on that?
Sure you can.
Cool.
I was absolutely shocked when he said that. Just astonishing, really. That kind of disregard for flight safety was allowed to take place.
Yeah, it's similar to the comments made during a discussion at Autographica about 10 years ago, when I think it was Al Warden was being questioned. He was being asked about the re-entry procedure. Basically, he said of the flight director at the time, if we could do it, we'd take him out and feed him to a bomb. That conjures up that famous image, Dr. Strangelove, piloting the bomb down to Earth, riding the bomb, waving his hat. Great image, but it's going to destroy things. So feeding people to a bomb is basically, we didn't like what he was doing, whether it was to do with the difference between a direct entry and a bounced entry, where you bounce off the atmosphere to reduce the speed, which they didn't do on Apollo. So the same sort of attitude, we feed him to a bomb, seemed to be the prevailing view of the astronauts.
Given the way things were run under Lucas, I don't know how things were run under his predecessors, but it does make you wonder if, considering that kind of disregard that was going on, all these efforts to try to make things look rosy, try to sweep things under the rug, all these cover-ups that were going on, it does make you wonder how things were going on during Apollo program, considering that Van Allen had originally said things like the radiation would have been a massive hazard to the astronauts, and suddenly it's all clear. There's all these problems, suddenly they'll just go away.
Yeah.
It makes you wonder.
It's the old political thing, isn't it? Because I say something, it will happen. I mean, that's what we got in the UK at the moment with the government. We're going to do this, we're going to do that. Just because you say it doesn't mean to say it's going to happen that way. It's same in Australia, where you've got this ridiculous censorship of young people now. It seems to be causing a lot of problems. Just because you say you're going to do it doesn't mean to say it's going to work.
For the record, I should say that Beaujolais, he didn't believe that the moon missions were faked. He had actually worked at Long Island where they were manufacturing the LEM. He believed that if they were going to do smoke and mirrors, as he put it, they wouldn't throw all that money into this lie. I disagree to that extent. Obviously, they've thrown gobs amount of money into lies. Look at all the money they threw into the claims of weapons of mass destruction in Iraq, for example, and stuff. The government will throw whatever they can to push a narrative. I'm sure Beaujolais believed that the moon missions were real. He probably wouldn't have wanted to believe those sort of things. But of course, I wasn't going to, push him along those lines because he was driven to post-traumatic stress disorder. I didn't want him to give him something else to feel upset about.
Fair enough.
NASA has a history of being less than truthful about their screw-ups, just like they did on Apollo. They said the astronauts at Apollo, on the Apollo fire, died instantly, which is in fact absolutely not true. They died an excruciating, painful death as they were inhaling flaming oxygen. That's how they operated. That's how they still operate. Columbia happened for the same reason the Challenger happened, because you had two managers that were hell-bent to say that everything was okay and just come home. And they burned up and killed the astronauts once again, all because they canceled a $200,000 check of the vehicle from space and or from the ground. And one of the top managers, I think her name was Mia Hamm, canceled that request. Listen, we got such good optics that we can do stuff from space and from the ground that people would be horrified. I mean, they can tell you if you have hamburgers or hot dogs on a grill, from space. Mm-hmm. So they had the resolution capability to actually spot any damage that was there, but the decision was made by the program managers not to do it because everything was okay. How could 2 pounds of density foam cause any damage to the leading weight? Well, during that investigation, they found out that a piece of 2-pound density foam propelled at Mach 0.8 blew a hole in the leading edge of the wing that was approximately a foot in diameter. Mm-hmm. And so, once again, all the hype about flight safety was just a mirage, and 7 more astronauts paid with their lives for that mirage. I was furious when people would refer to it as an accident, because it wasn't an accident. Horrible disaster, yes, but not an accident. An accident is something that just occurs out of the blue. But when you have something that is known ahead of time to have a high potential of being a disaster, you sure as hell can't call it an accident just because stupid people went ahead and made a stupid decision. Mm-hmm. I would have really liked to have seen the 4 backhaul managers and the upper echelon managers at the Marshall Space Flight Center be charged with either voluntary or involuntary manslaughter. I would have really loved to have seen that happen, and the reason being is not because I wanted to get back at them, and please understand that that was not the motive and would never be the motive, but I wanted to get the attention of people in these positions that they cannot just cavalier make decisions based on their profit line, their profit motive, and disregard the number one priority in these programs, which was flight safety, without paying a price. So that's my personal feeling. I think that they made a mistake by not putting some of the people away during Apollo days, and they repeated that same mistake with Challenger and also Columbia.
I think we made it earlier when we were talking with Robert, but what Scott has found, who's searched so many of the PDFs looking for information, and what he's finding is that, yes, a lot of testing was done. There's no doubt about that. And reports were written, there's no doubt about that, and they showed up the problems that had been discovered. Because these were serious companies doing the research. And they say, yes, there will be problems. Now, one specific area was to do with the photographic film being used. Yeah, the photographic film was examined and it was tested under the conditions they expected it to be operating under, and found that it caused problems, that there was fogging of the film. There was damage to the film by the radiation, by the vacuum. The vacuum wasn't known about very much at the time. This was all written up. People knew about the difficulties. And as Scott has said, where are the PDFs showing what action was taken to overcome the discovered problems? And they don't exist. It's as if, yeah, we found the problem. This is what the problem is. With photographic film, if you put it under certain conditions, it will be damaged. Okay, accept that. Now, what have you done to overcome those problems? That research and those PDFs don't exist.
I think it was on What Happened on the Moon. David Groves did some experiments exposing photographic film to X-rays, low-level X-rays, and he found that even a small dose would have been enough to significantly fog the film.
Yeah, well, look what I did with this here. I mean, I put 1 roll of film. I took all the pictures, but I put it outside the microwave oven here. And I poked 2 chopsticks in the door switches. You have to shut the magnetron on. I just put it on for 1 second, put the film about that far outside the door on the counter, hit it with a burst, and look at it. This is that black and white film, that high altitude film, that 168, which I purchased. Look at how it fogged.
Interesting. I have a question. Have you been able to acquire any SO243 film?
I only had the 168.
Yeah, it's understandable. I would really love to see a cross comparison with the SO243 film. That is the film that they said they carried on Lunar Orbiter and also the Voyager missions. That film is actually considered to be more resistant to radiation than the film they had on Apollo. Apollo was essentially off-the-shelf film for all intents and purposes, whereas the SO243 supposedly can take up to 100 rads to become 50% fogged. Something about the additional layering that it has or something like that. I don't know the exact details. I found a document describing this film. I haven't had a chance to read it from start to finish, but it's very interesting that was specifically selected for the Lunar Orbiter because of its resistance to radiation. Even then, they still had it in pressurized vault, to make sure it would function correctly, and they would promptly develop it and scan it and send it, before it had any chance to get significantly damaged or whatnot. And so,
when you find that, send us a copy of it. I have every PDF file on the film out there, and I've never seen that.
Yeah, we were just looking at that this morning. I went over one of these documents with the film. I believe there was 10 rolls of film I bought. 3 were 168s. Apparently, that was the one that they were using to test with radiation, and they said it fogged, and I can concur that it fogged.
With all the PDF files I've got on film, the first development I've ever seen of them putting additional anything on a film for a coating to protect it in any way, shape, or form was after 1975. Because I want to see what the actual date was on this file, because there's so many updates.
That's the problem.
So many updates, and that's where the problem is, because I have stuff from the 60s when this is going on, and there was nothing about the film.
I do bring this up because I find it very interesting. You remember that interview with Jan Lundberg, who was talking about the camera. Oh, well, it must have been the film that was special, but then they spoke to J.P. Arnold about the film they used. He said it was essentially ordinary film. It must have been the camera that was special. So you put these two people in a room together, they probably would be, what are you talking about? I thought you had the material. I thought you had this, this is just weird. Neither of them understood that this film was unprotected, essentially, for all intents and purposes. And so when they talk about they were using ordinary film on the Apollo, if they got this film that's supposed to be radiation resistant, you would have thought they would have made that mandatory to carry aboard the Apollo missions. Instead, they're using off-the-shelf film.
That's not what he said. When David Percy had Doug Arnold on the show, and he actually said the only difference in that film was the grain was finer and the polyester film, the plastic, was thinner so that they could get 200 shots on the roll. But that's it. It just had a finer grain. No radiation protection, no high altitude film stuff, no anything. That's the only two things he said that they did to that film.
I just sent them some pictures of one of the cameras that they used inside the LEM. That's for Apollo 11. It even has, if you look at the one of them, it has the back of the magazine, shows you the film that's in that camera. It also has settings on the top of it. If you look on the top of it, for Earth, for the moon, for the Terminator, all of those distances are in there. They're listed on the top of it. And it also says, remove the slide before you put the thing on. That is one of the strangest things that it's actually printed on there. But that's one of the ones that they used inside. That's a Hasselblad that they used inside the LEM, not on the lunar surface.
I actually tried to get a hold of one of those cameras. As a matter of fact, I contacted the Hasselblad company, and this is kind of funny. They told me that the only cameras they had available were the ones that were supposedly left on the moon. He said to me, if you happen to go by there, just pick one of them up.
Try approaching Hasselblad UK, because they've got a replica which I've used on television. That's the one I photograph in the talk I do. I show the pictures of it. That chap who was in David's film, that was AJP Arnold, I think it was, who's the managing director of Kodak in the UK. So he should know what he was talking about, especially going to be interviewed by somebody like David, who knew the questions to ask. What was the film used? Where did it come from? And he got the answer he was expecting. Came off the shelf. Normal stuff, bit thin. You get 200 into a magazine.
People need to know about radiation because NASA makes it disappear conveniently. Moon rocks don't have radiation. This does. Oh, the Van Allen belts. Well, that's not a problem. oh, solar flares, those aren't a problem. We don't even bother to mention it. They're having stuff flying around.
This is the book that Renee had cited in NASA Moved America. It's out of print now. This is by John Malden. He had made similar statements in regards to how much shielding you would need, the extent that you would need 2 meters of shielding, to shield against the solar flares and the like. And so in cosmic rays as well, of course, the cosmic rays, their more immediate problem is the solar flares, because the cosmic rays they discuss about being an issue for longer missions. But of course, you can look at the data from Artemis 1. Even if you calculate for the days that the Apollo astronauts were supposed to be in there, you find that Artemis was still detecting much more radiation per day than Apollo. And that's despite it having 3 times as much shielding.
That's Artemis 1, isn't it? December 2014, which might explain why there's very little talk now of Artemis 2, which is supposed to be flying around the moon with 4 astronauts on board. Maybe they've been asking questions. What protection are we being given, Mr. NASA? We heard that radiation can be quite harmful.
I was actually at the press conference when everybody was asking questions about the heat shield because it sustained much more damage than they were expecting. There were huge chunks of it coming off it. And my question was about the radiation. I was looking at the solar weather. I was looking at there was like 3 solar flares during the mission. I had asked them what was the readouts as far as proton flux and energy. How well did this shield against those solar flares? And the guy, his name was Mark Hugh, if I recall correctly, he was the project manager for the Orion capsule. His response was basically, you know more about those flares than I do.
Shit. Wow.
It's very reassuring.
Really?
And he just doubled down on, we got detectors, we got shielding, and this will be very important going forward into this project. Not very reassuring. For all the other questions about the heat shields, they would give, detailed answers, lasting very many minutes and stuff, to each of the reporters. But in my case, my question, his answer was less than a minute. It was like he was just trying to get it over and done with as soon as possible.
Maybe the astronauts understood what you were asking, and they started asking their own questions.
But this one here is a great PDF to go over.
This is nice color photographs. This is not an original document of any kind, so I'm going to compare it against some of the originals, especially on these window seals. Oh, it's completely different.
But Raza said that as far as it goes for the seals, for the ISS and things like that, he says that is a special rubber that lasts at least 30 years.
Put it in a California sun at the beach.
But I'm more interested in that capsule going to the moon because that was in minus 11 to 12. Now, how the hell can a rubber seal that when Bill Demos at the university have to use those one-time metal seals when they go over -6?
Yeah, this is a nice updated document. No, I haven't seen this one. It has a whole new thing on the heat shield and everything else. It's even designed differently on this one for the ablative shielding.
I think the film document is also something worth looking at for probably a future discussion.
Yeah.